We've talked about spin in the z direction, and we saw that we could have spin up and spin down states, and that the spin was quantized in units of h bar over 2. Let's now talk about spin in the x direction, in another direction. So in the x direction, you can have, say, a spin right, just as you did with, say, spin up in the z direction. And we would say that spin right is an eigenstate of the x spin operator, so s hat sub x, with a positive eigenvalue, positive h bar over 2. So it has positive angular momentum in the positive x direction. Of course, this state is also normalized with itself, so if I take the inner product between the right and the right state, I get 1. I could also then have spin left, and just as with spin up and down in the z direction, I can only get, if I were to measure the spin in the x direction, I can only get spin right or spin left. Those are the only values that I can get. That's the quantum mechanics showing up. And the eigenstate of, or the spin left is an eigenstate of the s hat x operator with an eigenvalue of negative h bar over 2. And again, it is normalized with itself so that it is its norm is 1. And in fact, the spin right and the spin left states are orthogonal to each other. So if I take the inner product between right and left, I get 0. Now, spin up and down and spin left and right seem like they're completely unrelated to each other, but it turns out, and we're not going to talk about how we know this right now, but it turns out that the spin in the x direction and spin in the z direction are related to each other. In fact, we can write down their kets, the relationship between their kets, in the following way. So it turns out that spin up is a mixture of spin right and spin left, and spin down is a different mixture of spin right and spin left. The way we actually determine this is we do Stern-Gerlach experiments where we take a spin up state and then send it through a Stern-Gerlach experiment that allows us to see how much spin right and spin left is within that. And in fact, let's take a look at that. Let's take a look at a Stern-Gerlach experiment that's oriented not in the z direction, but it's oriented in the x direction. So here I have a magnetic field that's pointing in the positive x direction instead of the z direction as we had before. And we're interested in taking a state that starts with a quote-unquote randomized spin, by which I mean, again, I have a state that is not an eigenstate of the Sx operator, and so it is a mixture of right and left states. And I'm going to send this through my Stern-Gerlach experiment that's pointing now in the x direction. And just as with the Stern-Gerlach experiment in the z direction, I'm going to have a force on the particle, depending on whether the particle has a spin right or a spin left. And so there will be spin right particles will be diverted one direction, and spin left particles will be diverted another direction, and I can set up a bin or a detector there to detect whether I get a particle there or not. And it turns out then, the probability to get a spin right particle for this initial state that we have is 1/2. And the probability to measure spin left would also be 1/2. And so if you were to send a particle through, say 1 a second, that starts in this randomized spin state, you send it through 1 a second, then half the time you would get a spin right particle hitting your detector, and half the time you would get a spin left particle hitting your detector. So now let's imagine we again chain together some Stern-Gerlach measurements, but now let's chain together some Stern-Gerlach measurements in different directions. So let me start with a Stern-Gerlach that is in the z direction. I'm going to start with a state that doesn't have a well-defined spin in the z direction. So I'll start with a state that's a mixture of up and down states, for instance. And then I'm going to chain this together so that the spin up states, if there was a spin up state that were to be measured, if it got diverted along that path, I'm going to send that path down a Stern-Gerlach experiment in the x direction. And ultimately, I want to know what is the probability to get something that is spin right or spin left at the end of all of this. Well, I know that after I send my particle through the first Stern-Gerlach experiment, that I'll have spin up and spin down states, and spin up states will be going along the path that goes into the positive x direction, and spin down states are going into the trash. And so the wave function, if it goes through the Stern-Gerlach experiment in the x direction, must be spin up to begin with. And so then I want to know, what is the probability that I'm going to get spin right or spin left if I start with a spin up state? And again, it seems like you should get 0 probability, right? Because it's spin up, it's not spinning right, and it's not spinning left. But that's not quite how quantum mechanics works. And really the right question to ask is, what is the overlap between, or what is the inner product between, say, the right eigenstate and psi, and take the absolute value squared, which will tell me the probability of getting spin right. Or alternatively, what is the overlap or the inner product between the spin left and psi, take the absolute value squared, and that'll tell me the probability to get spin left. Now the wave function that's going into this Stern-Gerlach experiment in the x direction is pure spin up, and so that's why we've substituted for psi, we've just substituted the spin up state here. And so we really need to figure out, what do we get for the inner product of right with up, the bra and ket there. Well, I mentioned before that there's a relationship between spin in the z direction and spin in the x direction. And so there's a way to write, for instance, the up ket in terms of right and left kets. So in particular, the up ket is a mixture of right ket and left ket. And so in taking this inner product then, we want to insert this up ket here in terms of right and left, and then we can just look at the inner product between right and left and use the fact that the right ket and the left ket are orthogonal to each other. And so we only get a term where we get a right and a right here for spin right. And that tells us our probability to get spin right in this case is 1/2. A similar calculation tells us that the probability to get spin left is also 1/2. So oddly enough, we started with spin up, sent it through a Stern-Gerlach experiment in the x direction, and we found a 50% chance of getting spin right for our measurement, and a 50% chance of getting spin left for our measurement. And again, whichever one you get is random for any given particle when you make that measurement. But we know that the probability will be 50-50 for getting spin right or spin left. Ultimately, this is based on experiment, so you do the experiment, you see that you get 50% probability for spin right and spin left. And then you infer that, spin up must be a 50-50 mixture of right and left. That's how we came up with that mixture up above.